There was a question on a problem from chapter 6, section 1. I want to look at that one. It's number 37. Y prime is equal to xy. Let me work this problem the way that I want you to solve it as well on the exam. I will give you a problem from 6.1 where one problem will be I'll give you a power series, bless you, and I will ask the question, find the interval and radius of convergence. So that's one problem. And then the second problem from 6.1 will be a problem just like this, where I want you to solve using the power series, but I will also ask you to solve by a previous method as well. So, and I can only do that for differential equations where a previous method actually matches up with it. Section 6.2 and 6.3, that's not necessarily the case. So for this kind of problem, we can solve it two ways. We can solve it by an old method, and we can solve it by the power series. The good thing about that is you can definitely compare the answers if you know how to translate a regular term to a power series form. So if you can't go from one to the other, then you have two answers and you still don't know if they're the same or not. So first, solve by previous method. So with this problem, this is dy over dx is equal to x times y. We can separate the variables. So this is if and only if 1 over y dy is equal to x dx. So this implies that we have the natural log of the absolute value of y is equal to 1/2 x squared plus some constant. And if we exponentiate both sides, we have e to the natural log of the absolute value of y is equal to e to the 1/2 x squared plus c sub 1. So this gives us y is equal to c times e to the 1/2 times x squared, where c is equal to e to the c sub 1. So our answer, when we work the answer for the power series, should look like this. Well, you say, what is that? E to the x for the power series looks like the summation as n goes from 0 to infinity of x to the n all over n factorial. If it's e to the x squared divided by 2, very similar, you just manipulate that. So e to the x squared over 2 is equal to the summation as n goes from 0 to infinity. Replace the x with x squared over 2. So this is x squared over 2 raised to the nth power all over n factorial. And you can simplify that. This is the summation as n goes from 0 to infinity. This is x to the 2n, and then times 1/2 to the n all over n factorial, and you can simplify that. This is x to the 2n all over 2 to the n times n factorial. Okay. So then the answer that we'll have would be some constant term times that summation, and so that constant term would be that capital C times the power series expression for e to the 1/2 x squared. So now, secondly, solving by power series, let y equal to the summation as n goes from 0 to infinity of c sub n times x to the n. And for this problem, we only have y prime, so y prime is the summation as n goes from 0 to infinity of c sub n times x to the n minus 1. And so we have y prime, what is that again? You know, this is the same thing as saying y prime minus x times y is equal to 0, right? So we can just say that. So here, this is y prime minus x times y. This is equal to the summation as n goes from 0 to infinity, c sub n times x to the n minus 1 minus x times the summation as n goes from 0 to infinity of c sub n, that's the n, times x to the n is equal to 0. For this problem, and what happens for the problems in 6.1 and 6.2, bless you, is that we don't have that index r like you have for 6.3 for the Frobenius. So for this one, you can check n equals 0 and see if the summation at that particular pivot is 0. And for that first summation, you do get 0 at n equals 0, because at n equals 0, you get c sub 0 times x to the negative 1. So it's safe to say here you can start this one at n goes from 1 to infinity. Remember, again, you cannot do that if you have a problem dealing with the power series for Frobenius, where you had the summation n goes from 0 to infinity of c sub n times x to the n plus r. That r index throws everything off. So here, this is the summation as n goes from 1 to infinity, c sub n times x to the n minus 1 minus the summation as n goes from 0 to infinity of c sub n times x to the n plus 1, right? Okay. That x was on the outside knocking on the door, and so we just invited him on inside, okay? And put him right next to his big buddy, x to the n. So they become x to the n plus 1. Well, so now we're going to say for the first summation, let k equal to n minus 1. For the second summation, let k equal to n plus 1. Let k equal to n minus 1. And then over here, let k equal to n plus 1. Okay. So we have the summation now as k goes from, n starts at 1, then k is equal to n, or 1 minus 1, that's 0, to infinity. C sub n becomes c sub k plus 1 times the n, but n is k plus 1, times x to the k, minus the summation as k goes from, well, n here starts at 0, so if n is 0, k goes from 1 to infinity of c sub n, and here this n would be k minus 1. Times x to the k is equal to 0. Okay. Now, I want to be able to write both summations as one summation, but I can't do that. Two things have to happen. X to the nth power, or the k, have to be the same term. Well, we do have that. We have x to the k here, x to the k there. But then secondly, the summations must start at the same position. This guy starts at k, goes from 0 to infinity. The second one goes from k, starts at 1 to infinity. So we're going to evaluate the first summation at k equal to 0. So when we do that, we have c sub 0 plus 1 is c sub 1. If k is 0, then we have x to the 0. And so now we say plus the summation as k goes from 1 to infinity. So now everything starts at k goes from 1. So now I can factor. This is x to the k. And what I have on the inside, just one summation, c sub k plus 1 times k plus 1 minus c sub k minus 1. Close that up. That's equal to 0. Well, straight off the bat, we're going to get c sub 1 is going to equal to 0 because the left side must equal to 0. So this implies c sub 1 is 0, and c sub k plus 1 times k plus 1 minus c sub k minus 1 is equal to 0. So we can solve now the formula for plus 1 equal to sub k minus 1 over k. So now looking at this formula, if we start at k is equal to 0, we get c sub 1 is equal to c sub negative 1 all over 1. But we said here that c sub 1 was equal to 0. Right. So what about c sub 2? That is for k equal to 1. So we get c naught all over 2. C sub 3 is c sub 1 over 3. But c sub 1 was 0, so this guy is 0. C sub 4 is, excuse me, c sub 2 all over 4. C sub 5 is c sub 3 over 5, and c sub 3 is 0. c sub 6, c sub 4 over 6. We had c sub 4 from back here, and so this is c sub 2 all over 6 times 4, c sub 7, c sub 5 over 7, c sub 5 is 0. Let's do one more, c sub 8, c sub 6 over 8. And I need to go back because c sub 2 depends on c naught. Yeah, that's right. So this is c naught over 6 times 4 times 2. And so this c sub 8 is the c sub 6, which is the c naught, and that's 8 times 6 times 4 times 2. Okay. So now let's see if we can put that information together and form the solution. So y is set to be of the form c naught plus c1 times x plus c sub 2 times x squared plus c sub 3 times x to the third plus, and so on. So y is equal to, so the c naught this guy right here, and that stays the c sub 0, then we'll go from all the way to c sub 2. And the c sub 2 is c naught over 2. So this is here. I'm just going to just put that in there for the time being, times x plus x squared is times c naught. C naught times x squared all over 2. I think the x to the c sub 3, I believe it went out to 0. It did. And then c sub 4 was the c sub 4 c naught over 4 times 2. Plus 0 times x to the third plus c naught times x to the fourth all over 4 times 2 plus, you kind of see the pattern, c naught times x to the sixth, and this is 6 times 4 times 2. Put one more in there, plus c naught times x to the 8th, and I believe that's 8 times 6 times 4 times 2. Plus, should be able to see the pattern. That x to the 8th, the previous was x to the 6th, the previous one was x to the 4th, previous was x to the 2nd, so that's x to the 2n. See that guy? And then the bottom guy is picking up the factorial, but it's the even factorials, right? So basically that's 2 times n factorial downstairs, right? So this is plus c naught times x to the 2n all over 2n factorial. And so we have y is equal to c naught, this is 1 plus x squared over 2 plus x to the 4th over 4 times 2 plus x to the 6th over 6 times 4 times 2 plus x to the 8 over 8 times 6 times 4 times 2 plus and so on. And that's it. Right? And you can look at that and compare that with the form for the previous method solution. And this guy here would be identical to what we have over there. So that 2 to the n times the n factorial, you can do some manipulation and show that this guy should look like the 2 times n factorial. Is there a question? So are you saying that WebAssign was asking for that answer in a certain way? Is that what you're saying? Now, for me, on the test, I'm satisfied with this answer right here. You're done. Okay. So was there an issue in WebAssign? Okay. Okay, no, this is fine right here. Just leave it like that. Yep. Yeah. You know the back of the book and how they do their answers, they try to make them look so sophisticated. And just if you just write the terms like I did right here, so for my terms downstairs, you get the 2 and then the 4 times 2 and the 6 times 4 times 2 and so on. Easily, if you take a calculator, just a simple calculator, calculate these values, and then if they have some sophisticated term like 2 to the n times whatever n factorial, and simplify that, you're going to get the same thing for each of these terms here. So that's fine. Okay. Any other questions? Alrighty, for the test, test 4. So number 1, so on number 1, I'm going to ask you questions in terms of being able to determine whether or not for a given power series, if you have ordinary or singular points. So determine ordinary singular points for a given differential equation. Number 2, determine the regular and irregular singular points. Number 3, determine the interval and radius of convergence. Number 4, solve a given differential equation by a previous method and also by the power series method. So that's section 6.1. Number 5, solve y double prime plus plus 2xy equal to 0 by power series. By power series expansion. Same thing, power series method. This is section 6.2. And then number 6. Solve 2xy double prime minus y prime plus 2y equal to 0 by the method of Frobenius and that's section 6.3. And that's the test. Just put some examples there, like numbers 5 and 6, example type problems from those sections in terms of how I want to phrase my question to you. Yes, Lawson. Yes, sir. Okay. Yes, sir. Mm-hmm. Yes. Mm-hmm. Okay. Yes. From the interval that you produce, that's how that term, that number that you have from the interval would give you your radius. Want me to take a problem here and work for you? I think I did number 1. What about I mean, I can look at number 5 if you want. That looks to be more complicated, and I can work that one and show you. Is that okay? Okay. Yes, sir. Yes, sir. Chapter 9. Mhm. I don't know if I put the integrity videos for calculus in the DE. Okay, yeah, okay, okay, and I know I do stuff and I forget, and so I think I just probably put everything in there. And, yeah. Okay. What? Let me work this problem, and then we'll look in Blackboard and see if we can pull it up for you. It shows it. Okay, it does. Is it where you click on integrity classes to go there, or yeah, okay? I know I have it there, and I should have everything. Calculus 1, 2, and 3 should be there. So if you click on integrity classes in Blackboard, you should be able to see everything from calculus. Oh, which section you're asking? Oh, okay, yeah, no problem. That would be 9 point, the power series. For some strange reason, 9.6 is just sticking in my head. I don't know if it's because I was looking at Genesis chapter 9, verse 6 this morning, or but I think it's chapter 9, section 6. And if you just take your calculus book and just look up power series, it'll take you right. Not power series, a ratio test. It should take you right there to it. And I think it's 9.6 because I think I broke that chapter down into two tests, like 9.1 to like 9.5, and so you don't want to look at that. I think it's 9.6 to like 9.9 or 9.10. I think if you look in that content, you'll find it because I remember for that test, the same questions were asked. Find the interval of convergence, and we're doing the same thing. So let me look at number 5 here, and we'll see how that works. This is number 5 from 6.1, where you're asked to find the interval and the radius of convergence. So we apply the ratio test. Which is the examination of the limit. It's typically from as n goes to infinity, but here we're dealing with k. So it's k to go to infinity of the absolute value of the a sub k plus 1 term divided by the a sub k term. Typically it's a sub n plus 1 divided by a sub n. And so we want to see whether or not this particular limit for the ratio test, you wanted to get less than 1 for convergence. Here, since we have this multiplier of x, then you can deviate or manipulate even the ratio test. So let's see. So this is the limit. As k goes to infinity of the absolute value. Now, if you will, we're taking the absolute value. So that's negative 1 to the k plus 1 divided by negative 1 to the k would give you basically the absolute value of negative 1, which the absolute value of negative 1 is just still 1. So we're just overlook that term. So this is x minus 5 to the k plus 1 all over 10k plus 1. This is all divided by x minus 5 to the k all over 10 to the k. So this is the limit, yes, as k goes to infinity, of the absolute value of, if you think about it, this is x minus 5 to the k times x minus 5 times 10 to the k all over 10 to the k times 10 times x minus 5 to the k. Is everybody okay with that? Okay. So the x minus 5 to the k cancels out, and the 10 to the k cancels out. So we have left the limit as k goes to infinity of the absolute value of x minus 5 all over 10. Now here's where we manipulate the ratio test. The ratio test said for convergence, you want the limit of the ratio to be less than 1. That's the ratio test, right? So I manipulate that, and I say here, I want this limit to be less than 1. Okay. Now you can do that because this limit, check this out. This is the limit as k goes to infinity. There's no k factors here, right? So basically this absolute value is a constant with respect to k. So the limit of a constant is the constant. So all I have left is basically the absolute value of x minus 5 divided by 10 is less than 1. Okay. So this implies, just solve it. Yep. So this implies that this is the absolute value of x minus 5 all over 10 less than 1 multiplied through by the 10. So we have the absolute value of x minus 5 is less than 10. And by definition, that this is defined as negative 10 less than x minus 5 less than 10. Adding through by 5. So we have negative 10 plus 5 is negative 5 less than x less than here 10 plus 5 is 15. So the radius is equal to 10. Excuse me. I added a 5. That's right. That's negative 5. This is negative 5. All right. So you want to check x equal negative 5 into this guy right here. So this is the summation as k goes from 0 to infinity. Negative 1 to the k. Plug in x equal to negative 5. So here we get negative 5 minus 5, that's negative 10 to the k all over 10 to the k. Let's simplify this. This is the summation as k goes from 0 to infinity. This is negative 1 to the k. That negative 10 to the k is negative 1 to the k times 10 to the k. So what we have left. Now, negative 1 to the k times negative 1 to the k is negative 1 to the 2k. That's just 1. So this is the summation of just 1 as k goes from 0 to infinity. And that's equal to infinity, so that diverges. So what about we check at x equal to 10, 15, I'm sorry. We check at the endpoints, negative 5. We check at 15. Summation as k goes from 0 to infinity, negative 1 to the k. It's x minus 5, so it's 15 minus 5. We get 10 to the k all over 10 to the k. Gives us the summation as k goes from 0 to infinity of negative 1 to the k. This guy also diverges. Because the limit here is unbounded. It oscillates between negative 1 and 1, right? But it never stops, right? It keeps on going. So if that be the case, then the interval of convergence is the open interval from negative 5 open at 15. Okay. Oh, you asked the question about the so-called radius. Well, do you recall that the form is x minus x naught, the absolute value of that is less than some number r, right? So if you manipulate this right here and multiply both sides by the 10, you get the absolute value of x minus 5. Remember, it's centered at 5, right? Is less than 10. So r is equal to 10. Yeah. Right, yep. Yes, sir. No, you're fine. You're fine. Yep. Okay. Any other questions? Yes, sir. Mm-hmm. Yes. You said right here 1 to the k. It's just 1 plus 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 1, right? That's what that is. And that's equal to infinity. Because if you notice that everything here canceled out, right? Negative 1 to the k times negative 1 to the k is just 1, right? And then 10 to the k divided by 10 to the k is just 1. So it's a summation of 1. So you're adding up 1 infinitely many times. Yep. And for the limit, for that second one, as you check as x is equal to 15, here you have the summation of negative 1 to the k. The limit must be monotonic. It either must increase to a bound or it must decrease to a bound. This guy, when you deal with negative 1 to the k, is bouncing up to positive 1, it jumps down to negative 1, and it keeps on going on, oscillating forever and ever. So it's not monotonic. The limit of a series, it has to travel in a certain path. Either it's going to increase without bound or it's going to decrease. I'll say not without bound, but it's going to increase with a bound, a limit, or it's going to decrease. It's going to stop at a number. But going up and down like that, it cannot be contained. Right? It's not stable. Yeah. It's an alternating series. Yes, sir. And you can apply the alternating series test. Alternating series test said that in order to determine if a alternating series is convergent, you check two things. Check the limit of the sequence. What's the limit of 1? The limit of the sequence for the alternating series test, we said it must equal to 0. That limit must be equal to 0. Well, there it fails. Then the second criteria for the alternating series test to be convergent is that the series is said to be monotonic. Either it's increasing or decreasing. And 1 is fixed, so it's neither increasing nor decreasing. Okay? All right. Any other questions? I tell y'all pull one on me, I tell you. I'll tell you why when I close this out.